Welcome to this session that is particularly close to my heart. Ever since we joined Dyalog, I've been pleading with Morten and other powers to get the rank operator into Dyalog because it's such a convenient way of thinking of data. So I'm very happy to see Roger here today proposing to you and to Morten is not even here, but he knows about it. That
we know who's the boss.
Yeah, the rank operator. And one thing, and think about it while Roger presents, I think this is particularly expressive in terms of parallelizing your computations. So try and think about it in that light as well. Roger?
Thank you, Kita. So this is how I propose to proceed. I'll do some examples executed in Dyalog APL using a model of the rank operator. And hopefully these examples would show you that the rank operator can be a useful thing. And then I would present the model as defense, and then go into it a little bit. And then look at 3 applications of the rank operator. And then talk about IRS. And close with a brief history. So here's some data, a 3x4 matrix of random numbers. And then I say sum rank 1 of the data. That means apply sum to the rank 1 objects of the argument, namely the rows. Okay. Now, in this case, you can use the axis operator to do the same thing. So it's just plus / axis 1 applied to the data.
Oh,
yes, index origin is always 0. And index origin should always be 0. So you can apply other functions to in the rank operator to the data. For example, grade up rank 1 on the data. So as above, you can see that R, capital R, is a dyadic operator. And that little plus symbol is just to get around the stranding of the 1 in the data. I want 1 to be an operand rather than an argument to plus. Okay. So grade up rank 1 on the data. So it applies grade up or upgrade. I can never remember which is the proper name, but grade up on each vector or each row of the argument. So can you do the same thing with axis? No.
Is that fun? What's the short answer for why you can't do that?
Because the axis operator is not really a proper operator. You can't, I don't think you can model it, for example.
You can split it.
It's not really an argument.
Sorry?
The word isn't really an argument. To
No, it's more than just the symbology. I mean, you can invent a symbol for axis operator, and I believe you still have the same problems with.
But they could have.
For grade up, they could have.
The thing is that they just did something they left out. And I
Yeah,
agree that
yeah, but it gets better. Yeah. Okay, so in the old days, this grade up rank 1, old days meaning before nested arrays, it's a challenging little problem to compute grade up on each row of an arbitrary rank array. So here's one way to do it. Basically, you laminate a row index to the ravel of the argument, getting a 2-column matrix, and then grade that, and then subtract the row index, and then reshape it, and there you have it. But it's not a complete solution because it just works for rank 1. What happens if it's rank 2, or if the argument is characters and so forth, then this function would work. And nowadays with nested arrays and the each operator, it's not too bad. Basically, you enclose the rows, apply grade up to each, and then is that mix the monadic up arrow? Okay. And sort rank 1. So I'm sorting each row. So notice I'm now getting into user-defined functions.
Roger.
Yes.
You're saying rank 1 in the rank operator.
Yes.
You have an option of saying 1, 2, etc. Is that part of it? Or
Yes. Yes. Yeah. I'll come to an example with that kind of thing. Okay. And again, it doesn't work with the axis operator. And average. So you can say average rank 1 on the data, you get the row averages. And it doesn't work with this axis operator. I can say average rank 2, average rank 0. Apply average to the scalar, so the average of each scalar. So I'm going to make a slight detour and look at this average computation. I have average already defined in the workspace, and I would now define average the way it's usually defined. So far, so good. Oh, and this version is the one you usually see. I've seen it in vector. I've seen it twice already at this conference, most recently this morning. So, and so average 1 each. So what's wrong with this last answer?
So many gaps.
Yeah, this the leading blank is a sure sign that there's some problem somewhere. And okay, I have data, the same data in the workspace. So let's say average rank 1. You get a 3x1 matrix. Whereas with the more complicated average that I did before, you get the proper 3-element vector. So one of the things that the rank operator does is to encourage you to be more careful about the shapes of your results. The problem is that you're dividing, in the vector case, you're dividing a scalar by a 1-element vector, getting a 1-element vector result. And in the rank operator, you do that 3 times. So you have 3 one-element vectors, and it's, of course, the rank operator will do the proper thing, which is to give a 3x1 matrix, but it's wrong. And what's wrong is not in the rank operator, but in the way the average 1 function is defined. Yes?
This is a flaw in APL. It's something I think should be taken out, is the treating of one-element vectors or matrices as scalars.
No, you're wrong. York APL had that, and it's like, it's a mess.
The problem is that the average function is written in a way.
Yes, yeah. It's not in the language. It's in the definition of average, which I know you'll all go away and never write it like that again. Because there are more problems. So, what's the average of 5? Fine. What's average 1 of 5? This last example is one that my boss got me on 33 years ago, 34 years ago when I was a summer student. And I have never forgotten it. Lip Gibson, in case you're wondering. Yeah. And more problems. Is that right? Yeah, okay. I stepped on my own point, because for that to happen, quad div has to be a non-default value. So suppose I do the default value of quad div, and then I say average 1 iota 0, you get 1, which is, I submit is not the right answer for the average of an empty vector. The same problem with the more fancy average that I wrote before. So, we have to be very careful when we tell people that this is the very best APL expression. Do I have time? Yes, I have time. However, in J, this is the very best J expression. So average of iota 0 is the correct answer. Average of a scalar is the correct answer. Average of average rank 1 of data is not a 3-column matrix, 3x1 matrix. Yeah. So, okay. So I hope it gives you a sense that the rank operator is a handy way to apply a function to
What's that rank 2?
average rank 2
Yeah, why does that keep for all size?
because it's an average of the rows. And there are 4 columns. The rows are the objects.
I thought it would take the average of
Yeah.
Yeah, okay.
It's the same as
Yeah.
Okay. Yeah.
Yeah.
So it's a handy way to slice and dice
Yeah.
the data in different ways. Sorry. I'll get to that. It's a model written in Dyalog APL. So so far we've only been applying dyadic functions to data in the rank operator. Now let's try, so far we've only been applying monadic functions. And now we apply dyadic functions. And this is saying concatenate rank 0, 1. And the 2 numbers indicate the left rank and the right rank. So on the left side, I want to apply to scalars, and on the right, apply to vectors. And this is what I get. Each, a scalar to a vector, next scalar to the next vector, next scalar, next vector. And you can also have negative ranks, meaning a rank which is 1 less than the rank of the argument, or else 0 if the argument is a scalar, rank 0. So it's the same thing because negative one rank on a vector is the same as rank 0, and negative 1 rank on a matrix is the same as rank 1. Sorry.
Is there any way to use a rank operator if you wanted to apply the function along columns of matrices?
No. You have to transpose the data.
So
Or
it seems to me like this
arrange the data correctly. Then you don't ever need to do that. Yeah.
the rank operator is fantastic. I'm using it for anything else. I love it. But it occupies space that the closed axis operator is an axis operator. And I think you really need to have both. A true axis operator and a rank operator combined would be amazing to do both the language.
Yeah. In that case, I think you will be amazed because there's no way the axis operator will be gotten rid of from Dyalog.
I'm talking about implementing another operator which is a true axis operator.
Is that possible?
What's that?
Is an axis operator possible?
I don't know.
Okay. Well,
You might want to talk about the transpose.
I said that. Yeah. If you transpose the data, then you can apply the rank operator and then you transpose it back. Yeah. Sorry, Bob?
Very expensive.
This brings up the question I wanted to ask you before, which is, I've been unable to figure out how to apply the rank operator to emulate laminate on, say, 2 vectors. So I can get one of them, I can't get the other. Comabar.
Yes.
Comabar rank something. Okay, how do you use the rank operator to get the 2-row matrix that laminate will produce? And these are vectors, so there's no issue of transpose or anything like that.
Sure there's. Where's transpose?
This
Okay.
comes more.
No, my question was how do I use the rank operator? Just the rank operator. That's all.
Well. There it is.
question is, how do you use just the rank operator? Not transpose end of the function, but just.
Okay, you can't. So you shouldn't do it.
Okay, that's
In terms of efficiency, it's nice to have the data laid out such that the rows are common because it's stored in row major order. But if you're trying to slam two vectors together and you have to use the transpose, you have to kind of undo that efficiency to get efficiency in the result. You've got to go through the transpose to get efficiency in the result.
All I can say is that your faithful implementer is more devious than you think. Okay, here's rank, catenate rank 1 to a vector and a matrix. So I'm saying apply to rank 1 objects on both sides. So apply one row to the first row, the same row to the second row, the same row to the third row. So it's this is a generalization of scalar extension. So it's cell extension. When you only have one cell, roughly speaking, when you only have one cell on one side, it's extended to have the same number of cells on the other side.
That works just as easily if you had the matrix on the left.
Yes.
That's right.
Yeah, I won't show it because it's pretty trivial. So, and I mentioned rank -1 here, so whoops. What happened? Yeah, no, it's the first law of demos is that things, okay. Okay, never mind. Okay, so now I'll go to the model. So all the fuss and fury is just this one page of code. That's all it is, or most of it. So here's the rank operator. There's the right operand omega omega can be one element or two elements or three elements, and they'll reshape it to have three elements and then initialize M for the monadic rank, L for the left rank, and R for the right rank. And then depending on whether it's being applied monadically or depending on whether the derived function is applied monadically or dialectically, do this line or this line.
Is this in the memory cell?
No,
Mistake?
not yet. There is a model of the rank operator in the defunds workspace. It's called rank. I think Phil Lass is the author of that. I don't think it's as clear as this because Phil jumps through hoops to avoid saying 0 equal cut NC alpha. Yeah. I try to go for clarity rather than, other considerations. And F rank means effective rank, and cells is a function that gives you the cells, and assemble is a thing that kind of harmonizes the result at the end to compute, harmonizes the results from each individual cell, or the application of the function to each cell. So it harmonizes the individual cells into an overall result. So let's look at that in action. here's the same data plus slash rank 1. So the first thing inside the rank operator is it makes M, L, and R. And omega, omega in this case is just 1. So M, L, and R are all 1s. And the next thing it does is it uses its monadic application, so it uses the rank and then sells to the argument. And to see that more clearly, use the disp function. So these are the argument cells relative to that rank. And inside of cells, it computes an effective rank, and in this case, it's the same as M, rank 1. And then to apply the function in the model, it uses summation each on the cells, and then assembles the result. In this case, assemble doesn't have much to do, but in other cases, it could be doing lots of things. Another example, the catenate example, 0, 1, 2 catenate rank -1 to this matrix. So it reshapes the 1 rank into 3, makes a monadic and left and right ranks out of it. It's the dyadic instance of the rank operator, so it uses L and R. So now L is -1, so L cells and R cells gets the argument cells from the left argument and the right argument. And again, disp shows the cells in a more identifiable form. And inside of cells, it uses effective rank. So in this case, the effective rank is 0, where L is -1. So F rank, all it's doing is converting a negative number to be an appropriate positive number, or if it's a positive number already, make sure that it's not bigger than the rank of the argument. So you could be saying plus slash rank 10 on data, it will still be okay. And then uses the each operator in the model only. In the model, uses the each operator to apply the function to corresponding cells. And the disp shows you more clearly what's going on. So catenated the first cell on the left to the first cell on the right, second cell on the left to the second cell on the right, third cell on the left, third cell on the right. And then assembles the result. So that's what it did. And one of the things about having a model is that not only do you get something you can execute and try things out, but it gives you a vocabulary for talking clearly about these things. So you can say, what are the -1 cells of data, and it shows you what they are. Works on character arguments, the -1 cells of another matrix, the -1 cells of a 3-dimensional array. -1 cells are important. They're the arrays along the leading dimension of the argument. So if you have a 4-dimensional array, then those are the cells, the -1 cells. Okay. So now we get to so-called applications. I only show it for scalar functions, but it can work for any function, functions of any rank. So this is out of product plus, and to do that you say function rank 0 and basically infinity. Infinity in this case being 16 because that's the maximum rank you can have in Dyalog. So f rank 0, 16 in Dyalog is out of product for scalar functions f. Okay. Next application is inner product. You can use rank to do the key part in inner product. So here I have plus dot times. It's the same as primitive plus dot times. Works for other scalar functions. And in my British APL Association, I guess it was a conference, right? Earlier in June, I show how this view of inner product leads to much more efficient implementation of inner product. So the traditional method of doing inner product that you learn in school is row by column. This definition, this definition of inner product, in particular there's this mess, that's the function, and then rank 1 infinity basically. So it's saying take a row on the left and the entire thing on the right and then apply this mess function. Okay, and in my paper, it's also on Vector. I notice it's on the front page of Vector. You can get onto there. It leads to an implementation that's 10 to 20 or more times faster in the product.
Is that going in the interpreter soon, or the?
Oh, it's in version 12.1.
It already is.
Yeah.
Beautiful.
Yeah.
And does that work for any associative function or any commutative function?
It works for any scalar functions at least. Okay, and I can't get my head around inner products of non-scalar functions. But
I think the left function may have to be commutative because you do reductions in a different order. So if you had to divide dot something, you might get different answers, right?
no.
No?
No, you can get, well, I mean, if you care about the order, you can go from bottom up, right? Yeah, you get answers that are numerically the same. And one of the reasons why row at a time is faster than row by column is that it's cache friendly. You're not, because with row by column, for a large matrix, you could be missing the cache on every element of the answer. But if you want to know the details, they're in the paper, which, as I said, is accessible through the Vector front page. So the rank operator is a tool of thought par excellence.
Is it going into Dyalog APL?
It's in version 12.1.
Rank up?
No. Well, you can all, write to Dyalog and encourage them to have it in version 13.0, and I would be pleased. So the third application that I'm going to mention is monetic Comabar. In version 12.1, which is going to be released after the conference, monetic Comabar is going to be available. And this is an example of what it does. And what does it do? This is what the Dyalog documentation says about it, and also what the ISO standard says about it. So given those descriptions, when does this end? 3:45, okay. Okay. So given those descriptions, this is a pretty good implementation of it. You take the leading dimension, or 1 if the argument is a scalar. So that's the number of rows in the result. And the result is always a matrix, and the number of rows is the leading dimension of the argument, or 1 if it's a scalar, and then the product of the other dimensions. So for example, in this case, this number is 2, and this number is the product of 3 and 4. Okay? And it gives the same answer even for scalars. Now what does J say? Well, J is not shy about using a rank operator, so it can describe Comabar more tersely. And from that description, you can derive a model like this. If the argument is a scalar, then it's just 1-by-1 reshape of the argument. Otherwise, it's ravel rank 1 of the argument. And since I consider myself an artist, I'm going to make this shorter. So this is ravel rank 1 using the power operator. This is saying that if the argument is a scalar, you do the ravel rank 1 twice. Otherwise, you just do it once. Or if you don't care so much about efficiency, or even if you do, you can just say ravel rank 1, do it twice. Look, you can do tacit programming in Dyalog. So now I get to IRS. IRS is not something negative in this context. It stands for Integrated Rank Support. It was first implemented by Bernanke and Bezov in Sharp APL in 1986. And I described it in my APL 95 paper. What it is that it's saying that it's an implementation technique where the primitives are aware that they're being invoked from the rank operator and doesn't bother with constructing all the cells. So for example, if you say 0 in, what's the name of this squish squad? In squad, rank 1. So in other words, I'm getting the first column. So instead of doing what the general rank operator has to do, which is to construct each cell, only to throw away most of it and only keep the first element, you can just go ahead and just take the first element of each row. So it doesn't have to go through this laborious process of constructing cells and then getting the result. Since it's only an implementation technique, it gives the same answer, as if you didn't have IRS. And to show that, I have to go into J. So this is serial squat rank 1 data. So I'm going to generate a 100 by 100,000 floating point random matrix and do a benchmark. So with IRS, the time is that number of seconds and the space is 1856 bytes. And with no IRS, and it's no IRS because the interpreter can't recognize that and do direct support for rank in there. So IRS is good because this is a factor of like I don't know, 500 in time and a factor of several thousand in space, and basically the factor can be as large as you like depending on the size of the argument. And this last bit shows you that the extra complication, by having this convoluted function, should only have been a factor of 2 or so, not the factor of 500. So most of this inefficiency, or most of this gain in efficiency, comes from integrated rank support. So a brief history. It's just a history of first rather than a comprehensive history. Ken Iverson, in his 1978 seminal paper, described the concept of function rank. And in 1982, Arthur Whitney, on the train to the APL 92 conference in Heidelberg, invented the rank operator. And Ken No Fu He knows a good thing when he sees one and wrote up about it immediately and published it in less than a year later in Rationalized APL. And Bob Bernanke is a fast worker, and he implemented the rank operator less than over a weekend. Okay.
So what took you so long to get it out?
And it's also in the ISO standard, section 9.3.3 to 9.3.5. But just be aware that there's a serious mistake in the description in this ISO standard. So I'm coming to the end. I talked about the rank complex number implementation yesterday, and afterwards somebody came up to me and complained that it was dry and that I should tell some jokes. So I'm going to tell a joke, or try some. Here's my attempt at humor. So can somebody please ask me, are there any ideas worth borrowing from Jay? Any other ideas worth borrowing from Jay? Can somebody ask me that? Oh, okay. Thank you for asking that. Yes, there are. But this is only a 4-day conference, and there's not enough time to tell you all about that. Thank you.